It means it's time to start. So welcome to the session on Generative AI Demystified. So my name is Rob Barton. So I'm a distinguished engineer with Cisco. Do a lot of my work with AI right now with our AI team, and we're developing a lot of kind of amazing products, and hopefully you heard about some of that this morning in the keynote. What we're going to talk about today, though, is a little bit different. I'm going to take you through how generative AI really works. So we're going to break apart the architecture of language models, large language models, how they actually work, how they came about. And pretty much all of AI today, modern AI, whether it's image generation, sound generation, it's based on the same thing. It's the same type of architecture that we use in ChatGPT and LLMs, and it's an architecture called the transformer. So I'm going to show you how the transformer works. Normally, this requires a lot of math, but we're not going to have any math today. We're going to keep it really straightforward and try to make it intuitive and give you examples to show you how it works. We're going to show you the two main adaptations that we're using a lot in the industry, and we're using it a lot at Cisco, things where we can tweak the model to do things we want for us, so fine-tuning of models, so we'll show how that works, as well as something called RAG, which is the very useful way to do augmentation of the model to get specific data for you. And then lastly, in the last half an hour or so, we're going to go through examples how Cisco is using generative AI in our products. And we're going to talk about examples from security to enterprise networking to WebEx and collaboration. And I'm going to show you in a demo, and hopefully the demo works for each of these. You're going to see in live person here how it actually will work. So to begin, let's talk about language modeling. Oh, and by the way, there's one other late addition to this, which is not in the slides, but I'm going to talk about it through our presentation. Who's heard of a company called DeepSeek? Everyone's heard, because your stock portfolio crashed last week. So DeepSeek is an amazing company out of China. They have revolutionized yet again how we approach generative AI. So I'm going to explain to you exactly what DeepSeek is doing to get these advantages and these performance improvements as we go through this presentation. There's actually three different key innovations that they brought that has really rethought how we're going to build these language models. And I'll show you those three things as we go through our presentation today. So as I was preparing this presentation, I sort of wanted to look at the history of AI, and particularly neural networks. And it's interesting because this really burst on the scene in November the 30th, 2022, when OpenAI released ChatGPT, so GPT 3.5. And to be honest, it even astounded the architects at OpenAI how well it worked. Even the people that had built neural networks for years, everybody in the industry was taken back and surprised at how well it worked in creating and generating content. It astonished us. It was like we had finally discovered how thought can work, how language actually works. But when we go back and look at the history, it's far earlier than 2022. In fact, the early days of AI, this concept of a neural network first came in the 1940s. So 1943, two American scientists, McCullough and Pitts, they invented this thing called the artificial neuron. It was just a mathematical idea. There were no real computers to apply it to. Then, interestingly, in 1956, there was this conference in the US at one of the Ivy League colleges, Dartmouth, and they coined this expression AI, and it was the first time that a group of people had come together and began to create this academic field of artificial intelligence. And quickly, 2 years after that, Rosenblatt was really the first thought leader to build something called a perceptron, he called it. And a perceptron is really the ancestor of today's modern neural networks. So for decades, they started to improve this and make it better and better. Of course, there were no computers, there were no data to train these models on. In fact, even training itself wasn't really well understood until the 1980s. In 1986, a professor in Canada, Geoffrey Hinton, he improved, I would say, an algorithm called backpropagation, which is the way we use to train neural networks. So without backpropagation, we would not have ChatGPT, Siri, Alexa, or any of those other wonderful things. He just won the Nobel Prize in September, as you may be aware. So he won it for his work back in the 1980s, and ever since then, he's done a tremendous amount of research. The paper that really architected the transformer, which all of modern AI now is really following, was published in 2018 by Google Brain. Google Brain was founded by Geoff Hinton. as well. So he has a huge, long secular career and academic contributions. All the way, of course, until last week when DeepSeek makes another great big stride forward. So that's not even on this chart, but we're seeing continual advancements and improvements as we go through it. Along the top, so these are the academic scientific breakthroughs. On the top, if you can look at this later, these are the landmark events. So as the events changed, they followed the academic breakthroughs. So this sort of is the scientific research aspect following by the changes that happen as AI progressed. But you can just keep that for your reference. I thought it would be fun to just sort of create that as we discover how did we get here to this amazing place. Well, of course, 2 years ago, just over 2 years ago, OpenAI released GPT 3.5. It's probably the most monumental technical innovation, I think, of our lifetimes. We'll look back, I would think, in 50 years at that point and say this is a day that changed human history. We started to use generative AI, and it's only at its very beginning, at its infancy. We were going to see so many amazing things. For example, coding. At Cisco, internally, we use generative AI a lot. So a huge amount of our work now is done with things like ChatGPT. Debugging of code, it's almost, we call it superhuman in its ability to find problems, to debug quickly, to generate new code. Here's an example. I just did this one of something called a sigmoid function. We'll talk about that later. That's one of the main activation functions inside of a neural network. So I asked it in just one little sentence of English right there at the top, please generate the sigmoid and graph it, and that's all it does. It's amazing how well it works. You can ask it to do things like automation scripts. So if you're using Catalyst Center, if you're using any one of our automation platforms, you can ask it to please create the automation script for me. I can have it done in Ansible, in whatever language I would like. It will create it. I can move it in. Now, you're probably thinking, wouldn't it be nice if this was actually in Catalyst Center, if I don't have to go cut and paste back and forth? Well, we're going to talk about that a little bit later in the presentation, how this is actually coming natively into our products. And of course, this goes beyond language. We can also use it for images. So one of the platforms that OpenAI developed is called DALL-E. You can ask it to create images of things that have never been created. So create a picture of Albert Einstein competing at the Olympics. Of course, he never competed at the Olympics, but it knows what Albert Einstein looks like, and it puts him into a bib for racing. So it can create images like this, and I think we're very familiar with that. And there's many neat platforms around. So how did all of this come about? Well, we can trace back the origins of large language models to the 1960s. So in 1964 to 67, professor at MIT, Joseph Weizenbaum, he developed what we really recognize now as the first language model. He called it ELIZA. It's based on a character from a play called Pygmalion. And basically, you could ask it questions, and it would give you answers, and it felt like it was actually human. There's actually a story where Weizenbaum's own secretary was fooled to think that this was a real person and had an emotional connection with the ELIZA chatbot. This chatbot was not looking at understanding the words or really the language. It was just a very complicated graph structure. So when you put certain words in, it would use its graph to find the response, and it would take those words and put it back in for you. So it was very structured in a way. It wasn't like modern AI at all. It was a very rules-based mechanism. It was good for doctors to use. They actually could simulate a psychiatrist, is the most famous use case of ELIZA. But that is history. That is 50 years ago. People are surprised that language modeling goes back that far. Of course, we use language modeling all the time today. If you're using Instagram or Google or YouTube, when you start typing a word, it tries to guess what your word is. It tries to complete that word. And what it's doing is trying to take the digits or characters that you've given to it and using a probability distribution, what is the next likely word or character going to be? So we typically express it like this. So what's the probability of the next word based on all the words that have come earlier? And the way we do it is that we train it on a huge corpus of text like Wikipedia. So it looks at all of Wikipedia, and it just trains over and over and over again until it sort of knows which word is likely to come next if you give it a certain sequence. So if you go to Google, and you start to type. So I was going to type transformer, because transformer is the main AI architecture we're going to talk about. So TRA, and it types translate, translink, transductor, transformer, rise of the beast. It was not a very good movie, by the way. Translate English to Chinese. So it tries to predict what my next word is going to be. And part of it is based on my history and what's trending. But do you know what you're really looking at here? It's actually a probability distribution. Right? This is a probability distribution where the top is the highest probability of that word completion. So if you were to have a sentence like this and put it into a language model, I'll make him an offer he can't, and this is from an American movie. Anybody want to guess what the next word is going to be? I'll make him an offer he can't refuse, from The Godfather. What it's actually doing is looking at every word in the English vocabulary, all of the words, and giving it a probability. And it will give a probability to the most likely one, and refuse has a probability. Every other word has a probability. Most of them are essentially 0, but every word will have a probability in this prediction. Now, there's different ways that people have looked at this, and they're using neural networks to train on this, of course. And they use this thing called an n-gram approach. So you could look at 2 words at a time, 3 words at a time, 4 words at a time. The more words you have in a row, the more accurate your prediction is going to be. If I only had 2 words, he can't, it's very hard to predict refuse. But if I can make all these words together, it becomes more and more accurate. And one of the challenges we faced with neural networks was memory. So as you feed more and more words in, to have a memory of all those words was very, very difficult. Now, this is where the transformer came in. The transformer keeps a massive memory. It can keep a memory of hundreds of thousands of words. So it works very differently than the historical ways that neural networks were established. So what's really happening here is you're putting your prompt in. I'll make him an offer he can't. It goes into this big neural network, and you have an input layer here. These things in the middle are called hidden layers, and they're kind of crisscrossed with these connections. And out of the end, it has a classifier. And this classifier has a class for every word in the language. So let's say we have 100,000 words in English. There's going to be 100,000 possible outputs here. Every single one of those 100,000 gets a probability. We pick the one which has the highest probability, and it's refuse. So that's how typical historical language modeling works. Now, there's a little more detail to this. What's actually going on, of course, is you're writing a prompt, and the language model first has to think about, well, every word that you're putting in, I'm going to make those words into the smallest little component, a little thing we call a token, and take those tokens, and then I'm going to turn tokens into numbers. So a language model doesn't understand words. Words in different languages are not what it speaks. Neural networks speak in numbers. It's all mathematics. There's numbers attached to all those little circles and those lines that I showed you. So it has to convert your tokens into numbers. Once you have your numbers, it then passes it into the large language model like ChatGPT, and it can start to generate some content for you. So let's take this one step at a time so you can sort of intuitively see what's going on. Now, the first step I said is you take a word and you convert it into tokens. Now, this is an important step because the vocabulary, let's say the vocabulary of English, it's actually more than 100,000. It's more like 600,000 words if you look at all the historical words. If a language model was to be trained on every single word, it would have to see so many occurrences of those words to know how to use it. Well, what about very strange words like this? This is a medical term. This is actually the longest word, apparently, in the English language. It would have to see enough uses of that word to know how to use it. But that doesn't exist. There's only a couple occurrences. Probably nobody uses this word. So what ChatGPT does, it takes this word and it chops it up into little pieces of the components. These are like subwords. And you can see these subwords along the bottom. Those subwords are called tokens. And now each token sort of carries meaning. So it carries meaning how words can be broken down. Like the word Amsterdam is a combination of the Amstel River and dam. That's how this city was formed. It's 2 words that are put together. So the first job of any chatbot is to put these into tokens. So if you wanted to check it out, let's go to here. And we should be here. second to come over. And try it again. 3, 2, 1. There it is. OK, so just a little slow. So here's the OpenAI tokenizer. So here's this word that I put in. And you can see on the bottom, it's got it says 15 tokens and 45 characters. Now, this tokenizer is for GPT-4. The one I showed you in the slide was GPT 3.5. And now it says 17 tokens. So different language models have different tokenizers. It's how they chop up the words into different things. So let's take this out. Let's put in like Netherlands. Netherlands, and you can see that it's got the N plus Netherlands, 2 tokens. That's how it's decided to break up this word. You can put any word you want in, like let's say summertime, and it says summer and time. Basically, those are the 2 different tokens that make up that word. So the tokenizer is a very important first step. It has to break this up. Now, each token, if you put them all together, is the vocabulary of a language model. ChatGPT has a vocabulary of around 50,000 tokens. So that's much more efficient than having 600,000 possible English words, because now it's going to just look at what the tokens it needs. OK, so let's say we have 50,000 tokens that describe that are every single word of a language. Now, as I said, words, they're not in a language model. You actually have to convert this to numbers. So how do you convert a word to a number? How is a word expressed? Well, you could index them all the way. Well, the first word is A, all the way down to whatever this one is at the end. This could be a huge number of words. That's one way you could do it, but it doesn't really give you any meaning. What you want is for embedding the meaning mathematically. So when the people at Google were looking at this back around 2013, they started to realize that we need to have a high number of dimensions to represent a word. Well, how many dimensions do you think it requires to describe a word? Well, I'll give you an example. If you say to your child or your parents, you say to them, "I love you." So love carries meaning, doesn't it? Now, if you say, "I love Cisco Live," you usually use the same word love, but do you love Cisco Live as much as you love your child? Of course not. The meaning is very, very different based on the context. So how can you capture the context in the mathematical embedding? It's more than just an index number. So words carry different meaning, depend how they are used. So they developed this open source project called Word2Vec, so converting words into vectors of numbers. And they realized, well, we need to capture a lot of dimensions to understand all of those different meanings, the color, the texture of words in different ways and context. And they figured, let's create 300-dimensional vectors for every single word. So when we scan Wikipedia over and over and over again, it's going to start to fill out a 300-dimensional vector and learn those numbers inside the vector that describe the word. It's kind of like going to the dictionary, and you look up a word, and it tells you all the different definitions of the word. That's what we're doing mathematically through word embedding. So we're capturing all of that meaning, the context, the color, the texture, all different ways a word can be used in 300 different dimensions. This was the first time that words had actually been converted into numbers like this, because we knew we had to pass it into neural networks. When OpenAI started looking at this, they realized 300 is not enough. Words are used in so many different ways and so many different contexts. 300 doesn't give you nearly the creative ability to use a word. So they use actually 12,288 dimensions for every single word. So imagine that. That's a huge number of dimensions. Every single word, when I say word, I mean token, in the vocabulary to describe what is used in the language model. So that's pretty impressive. So I want to show you sort of intuitively sort of what this means. So if I look at a vector and I take a vector and I put it into a graph, what does that mean as the language model starts to learn? So there's a very nice visualizer that we have for Word2Vec, and I'm going to show you just what this looks like. Okay, so this is the Word2Vec embedding projector. And all these little dots, they represent a word. So imagine once I've learned the vectors for a number, so a number now represents many 300 dimensions represent a word. I can project it into a space like this. So we call this the semantic space for words. And all these are words. Now, what's interesting is when I start to put a word in, let's go back. Let's put a word like king. So it's king, I'm gonna click on it. And do you notice all these words down here around king? They're kind of similar to king, like duke, crowned, emperor, throne, fought, archbishop, assassinated. In the language that is learned by looking at billions and billions and billions of words, as it puts those numbers into the vector, the numbers around king have related words. They could be synonyms, they could be words that are closely related. So graphically, words that are similar or used in a similar way are always going to appear around the same place. Now, this might seem a little abstract to you, but this is the essence of how generative AI works. So when you start to put in a prompt, it finds the word in the space, and it's predicting in this space where the next word is likely to be. So it all comes down to this graphical semantic relationship between words. So you can play with this later, but it's a fascinating tool because you start to see interesting properties emerge. For example, words that are similar, like big, large, huge, are all going to be grouped in the same space. Different words like math, numbers, calculus, they will be in the same space. Words that are their opposites, like big and small, will appear on opposite sides of this semantic space. So what they sort of discovered is that language has a mathematical formation. And people didn't really think about this before. We just learned, well, languages are hard to learn. I have to practice it. I have to study it. When we started applying this with neural networks, we discovered languages have a structure that can be resembled mathematically. And once you start to study this mathematical relationship, it's a fascinating thing. So you pick any words that are similar, you're going to see them in a similar region of space in that three-dimensional graph. Now, it's actually much higher dimensions. We're just collapsing the dimensions to see it in 3 dimensions, but it's to give you this intuitive idea. So I want to give you this example. When I look at the word king, the vector for king in that space, it appears in space around here. Now, if I subtract the vector for man, I remove it, I still retain some of the value of royalty in that vector. Now, I'm going to add the vector for woman, and what does it end up with? It ends up in the same place as queen. So you can start to see there's a mathematical relationship with words if you represent them as numbers. And this was fascinating. Nobody knew this before. But once you started to do this, it allows us to create products like ChatGPT because we can mathematically predict one word after the next because there is a mathematical relationship with words. And it turns out there's a mathematical relationship with images, with pixels, with sounds. They're all exactly the same. All of these generative AI applications follow the same principles. Okay, so how do these neural networks actually do this? How do they work? So here's a neural network. So we have an input layer, and the input layer has things coming in. So these are the numbers that I showed you, those vectors. They will come into these neurons. They'll be processed in a hidden layer. So this is a little mathematical function. Remember I showed you that sigmoid, that S, sort of the beginning? That's one of the things going on inside this blue dot. Then they will come out to an output layer. If this is a language model, the output layer has a number of dots that equals the number of the vocabulary of the language. So ChatGPT uses a vocabulary of 50,000 tokens. You would have 50,000 of these dots at the output layer as it predicts the next word. Okay, so that's cool. Go through this. So let's take this little sentence here. Houston, we have a problem. Okay, this is from the Apollo 13 story. I'm going to put this into my neural network. And every word, Houston, we have a problem, every word is converted into this number vector. So I showed you that word embedding. That's where we convert words into numbers. So here's the vector. Each one will go into its own neuron. So how many neurons would you have on the input? Well, it equals the number of words that I can put into my model. So we call this the context window. So for example, in ChatGPT 4, we can put, I believe it's 8,000 words in. So this would have 8,000 blue dots entering the model. You have very big ones like Anthropic Claude has over 100,000 in the context. So we have 100,000 of these blue dots that allow these words to come. You can put a whole book. A whole book could come right into this neural network here at the entry level. So they're passed in, and then they go to this hidden layer where a little computation happens. So they're passed in, and each of the neurons in the hidden layer has a little function, a little job to do. For every connection that comes in, and it's usually fully connected, there's a weight. The weight is just a number. The weight is a number that's typically 16 bits long. We call it a floating point number. That's what's learned through training. So when you train your model by going through billions of different words, it's learning these weights, weight 1 all the way down to trillion weights that could be in a big model. So this training of the weights, that's what Geoffrey Hinton really discovered and was able to publish. He figured out the way to learn these weights with backpropagation, which allows neural networks to be used. Now, we use, typically in networks like this, 16 bits. I'll show you the first innovation of DeepSeek. They found a way to do this with less data. So if 16 bits is being learned, that has to stay in GPU memory. So if I'm using 16 bits for, say, 1 trillion parameters, that's a huge amount of memory. It all goes into GPU memory, into their VRAM. What DeepSeek did is they found a way to do it with 8 bits. So they reduced the number of bits on these weights by half in many cases. So they immediately reduced the amount of memory required in GPUs, which all of a sudden means half as many GPUs are used. So with DeepSeek, what they published is that they were able to train a model equivalent size to ChatGPT with only 5% of the GPUs. 5%. So that shocked the world, because this means, does NVIDIA sell 95% less GPUs? I mean, that's why the stock market crashed the next day, and big companies that held data center, they also crashed. Now the reality is, this was inevitable. It was going to happen. People were going to be able to innovate and find better ways to do this. I think about it like in the 1980s. IBM had these big mainframes, and they were huge, expensive computers. But then people came and invented servers and much more efficient computing systems. Did we buy less compute or more? We bought a lot more. So what DeepSeek showed us is there's faster, better ways to train these models. We're just going to buy more of it. It makes it more accessible for all of us to go and buy these things. So that was the first thing. They found a way to use less weight, less bits in the weight. Now, once these weights are coming in, they multiply by the value that entered the neuron. So whatever, for Houston, all those numbers get multiplied by the weight. We add them all up. We add something called a bias, and then you pass it through a little mathematical function called the activation function. And this just normalizes it. This is called the ReLU, rectifier linear unit. Anything left, any negative number just gets flattened to 0, and then anything on the right-hand side will come out whatever value. So this gets passed from one neuron to the next, to the next, to the next, until finally it pops out and selects the word problem or something. That will be the way that it works. So mathematically, your words, as they go in, are going through this function every single time. So how much is going on here? How much math is involved? Well, if you count it all up, this is a very small neural network. I call this a toy, just my little toy neural network. Just a small number of neurons, 7 here, 4 here, 3 there. Those weights, there's 1 weight for every line, and 1 weight for every line here. So 4 times 7. That's 28, plus there's something called a bias. The bias is just an adjustment to make sure the weight is right. So there's 32 parameters here, and there's 15 there, which gives us a total of 47 parameters in my little toy network. Now, when you look at GPT-4, it's a trillion parameters. So just imagine the scale and size of what the neural network looks like for ChatGPT-4. Or Anthropic, or Mistral, these massive, huge language models. In fact, if we go back and look at the growth of language models since 2018, they've just gotten bigger and bigger and bigger. They're absolutely astounding in size. Okay, I'm going to give you a very silly example here. Neural networks were inspired by the brain. So we have neurons, and we have synapses that connect our neurons. That's sort of the inspiration for neural networks, but it's not the same way that they work. But it's fun to kind of compare. If you look at how many neurons the human brain has, it's around, say, the synapses we have 86 billion, trillion synapses, and we have around a billion of these neurons. We compare this with the largest language models, so we have 100 trillion of these in our brain. The biggest GPT-4 probably is around a trillion parameters. We're still like 100 times more synapses in our brain than the connections in the largest language model there is. And your brain fits in the size of your head, very, very small. You look at the size of the GPT-4 model, it was like the size of an airport to train a model that big. So if we can make this many connections in our brain, it shows that there's many opportunities for innovation. So this is exactly what we've seen with DeepSeek. They're finding ways to innovate very, very quickly. So these kind of innovations are going to keep happening. It just shows you we're at the very beginning of this journey. So when we look at the language models, they're doing way more than just predicting a word. They're predicting entire scripts. You can write code, you can write whole stories, write a resume, you can write a book probably with one of these language models. So how do they work? They're doing far more than just predicting a word. So they're using something called the transformer. The transformer is a neural network architecture that was an absolute game changer. It changed the world as we know it. It occurred in 2018 with this paper called Attention is All You Need. So this was by Google Brain. So all of these scientists at Google Brain, they worked on this idea. There's one guy who's not at Google Brain, Aidan Gomez. He was the student of Geoffrey Hinton, and he went on to form a company called Cohere, which is a competitor. They came up with this idea of the transformer that would completely revolutionize AI. So they published this, sorry, 2017. The first model appeared a year later in 2018. The transformer tried to fix this problem with memory, like remembering how many words are flowing into the model. But more importantly, it understood the context. So do you know I showed you that floating diagram of the word embedding where the words have a particular meaning? Well, that's just a word. What a transformer does is understands the context of an entire sentence. So we can actually embed mathematically what an entire story means in a big matrix. So mathematically, you're encoding meaning of not just words, but entire sentences and paragraphs. So that's what the transformer was able to do. It has two components. One is called the encoder, and one is called the decoder component. So the encoder we're going to go through that in a little more detail, and it's very similar to the decoder. Most language models are one or the other. For example, GPT-4 and all that family are just a pure decoder, and I'll show you exactly why in just a minute. So this is a picture of the transformer that came out of that paper in 2017. So this is the architecture that they proposed. So we see the encoder on the left and the decoder on the right. They actually had, I would say, 3 key innovations in the transformer. One was just the pure architecture of this type of model. No one had really built a neural network that looked like this before. And the second one is something called the attention mechanism. So we see multi-head attention. Attention is the way that we encode context and meaning of an entire sentence. So not just words anymore, but entire sentences and paragraphs and entire stories could be 100,000 words long. The attention head, the attention algorithm, is the way that we do that. It encodes it mathematically inside this piece here. The third piece that they innovated, which was really cool, is something called positional encoding. Once you have very long sequences, there's no way for a neural network to know where the word should be in a sentence. It gets lost in its order. When we talk, we intuitively know the order of words as it comes through. But how does a neural network actually know that? So they came up with a very cool algorithm called positional encoding, where they actually secretly embed where this word is in the sentence. Oh, this is word 5, this is word 10, this is word 2000. So you know exactly where the word places in that sequence. So this paper that they came up with was more than just one innovation. It was layer upon layer of amazing ideas that was completely revolutionary. So within a year, of course, we had the first model that came out. It was called BERT. We'll talk about BERT a little bit. It's a pure encoder model. And what encoder models do is they are very good at just understanding. So this is the encoder. It learns the meaning of text. It doesn't generate any text. It just learns the meaning, and it understands exactly what is said. It's not really able to go and write a story for you, but it understands through the attention mechanism what you've put into it. The decoder has everything here, so it has the attention head, but it also generates tokens. So it actually is able to produce content and write things as it goes. Now, you might think, well, why would I ever just use an encoder? I'm going to show you an example of a Cisco product that is an encoder a little bit later. So there are uses, very important uses for both of these, even though we might be very familiar with just ChatGPT. I'm just curious in the audience, who here is using ChatGPT or something similar on a regular basis? Okay, that's why you're here. Very good. So if your hand didn't go up, I highly encourage you to check it out. It's a very, very useful tool. Okay, so we're going to go through the mechanism, the mechanics of how the attention mechanism works, because this was the revolutionary idea that has made all of this generative AI become possible. So the self-attention mechanism is a way to embed context of words by giving the attention to one word to the next as it goes through an entire sequence. So when we look at words, words carry meaning, but that meaning can change when they're connected with other words. So take a look at these two sentences. Who is Snow White? So do you know the story of Snow White and the Seven Dwarfs? It's a very famous fairy tale story. I changed one word, who, to why. Okay, the other words is Snow White is exactly the same. But do you see how the words change? The word meaning has completely different intonation and different explanation now. So in this case, who is Snow White means there has to be a noun. It has to be a person's name when I say who. Now, if I say why, there has to be a verb because I'm asking a why question. So in this case, there's the verb, and the noun is changed. So here, Snow White, the two words is the noun, but here only snow is the noun. So this is a scientific question, whereas this is a question about a person. It's the job of the attention mechanism to understand the differences and to encode this. So what it's doing is it's looking at every word one at a time, and it says, when I see the word who, it means there must be a noun in the sentence. So it looks for where the noun is. And the only possible way you can find a noun that's a name is by combining snow and white together. So it said that must be the name that answers who. When it's a why, it means there has to be an adjective that modifies the noun with the verb. So why is a very different type of question, and it has to look for that combination to exist. This is what the attention mechanism does. So if I go to a language model, and this is Claude, and I put in who is Snow White, it comes up with a very nice explanation of Snow White and the Seven Dwarfs. If I just change the one word to why, now it tells me the scientific answer, why snow is white. It does this because of the attention mechanism. The attention mechanism is the way that we discover the meaning of the entire context of that sentence. So how on earth is it doing that? Because it's doing far more than just converting a word into a number. So inside the transformer is the attention mechanism, the attention head. And this is the most important part of the transformer. Every modern language model, every image generator, every sound generator in the modern AI era is using the attention mechanism. Okay. In the attention mechanism, it can get a little complicated. I'm just going to warn you, we're not going to go super deep on this because there could be a lot of math involved, and I don't want you to run out the door screaming. But I'm going to try to give you an intuitive sense of what's going on. We're going to step through it just to show you the steps one by one, what's actually happening inside of the attention mechanism. So importantly, the attention mechanism is based on these boxes. Every box is a different neural network. Okay? So it's not one big, massive neural network working together. It's blocks of blocks of neural networks that have different jobs to do and discover different things about the sentence that you've put in. Now, there's a Q, K, and V. I'm going to show you what these are. So imagine we've got our sentence, who is Snow White? Now, what's the first step when we type in who is Snow White? We tokenize, right? The tokenizer chops it up into different components of the words. Then the tokens get converted into numbers, right? Those word embeddings. So we talked about those steps, exactly the same. Now we're going to send those embeddings into the transformer. Okay, so the first thing is that embedding, who is Snow White, gets split 3 different ways. So it's 3 copies of the same thing. One goes to the top, called the Q matrix. One goes into the middle, the K matrix, and one is the V matrix. Each matrix here, each neural network, has a different job. The Q is to ask questions about every word. So for example, if the word is who, and it sees the first word who, what should it ask? Well, where's a name for who? Right? That's the question that should be asked. So the Q neural network is trained to ask questions. The K neural network is the answer. It's the key. That's why it's called a key. So query and key. Key will be, here's a name that answers who. So Snow White is the answer to who. So K is an embedding of the answers to whatever question is asked. V is the original. We're not going to change V. We're going to use it for later to bring it back home to encode the meaning. OK, so let's go through this. So we go through Q, and it looks at who. And K says, OK, I found an answer to who. It's Snow White. Right, but this is all in math. So what we do is the answer that comes out of these two neural networks is a matrix. And we simply multiply these two matrices together. So if you remember linear algebra from school, that's what matrix are. And we're doing something called the dot product. So it's a matrix multiplication. And we end up with a new matrix that is a result. And what this resulting matrix does, it gives us a very, very important result. It basically tells us what's important. Where should your attention focus? That's why it's called the attention mechanism. And when we do this, we see that Snow and White are really high. Like this seems to be really important to the answer of who. So it compares every word in that sequence. And so Snow and White seem to be the most important answers to that question. So that's what it needs to focus on. Snow White now is a person. That's the name. That's the answer that we're going to go and generate. Now, what we need to do is we need to smooth this out because this can be really big. So it goes into another block, another neural network that smooths this out. It's called the softmax function. Softmax is incredibly popular in AI. We'll see it in almost every AI model out there. Softmax is a nice way to just smooth things out and give a probability distribution to tell you which word is important. By the way, have you heard of this phenomenon called hallucination? You're all nodding your heads. You know what hallucination is? It's when your model picks the wrong words and gives you the wrong answer. Why does that happen? Why does it hallucinate? One of the biggest reasons is a property of these language models called temperature. So temperature is basically how much randomness is in your language model. Temperature goes from 0 up to whatever number you want. 1 would be considered a very good balance. It's going to give you nice answers. But if your temperature is too high, it's going to be just gibberish. So you go to temperature 4 or 5, it's going to be almost incoherent. We don't want language models to always give us the same answer. We want it to be creative. Like if you're going to write a story or something, write poetry with your ChatGPT, you don't want it to always give you the exact same answer. You want it to have variation. So that variation comes from having a higher temperature. If I'm going to ask questions about my network, I want it to be exact. So I'm going to have a low temperature. Now, the softmax function that's in here, that's where the temperature variable exists. So if the temperature variable is too high, all of these colored lines will almost be the same. So if it's going to pick one of these words out of this probability, it could pick the wrong one. And as soon as it picks the wrong one, it hallucinates. So the temperature variable in softmax is where most hallucinations will come from. So if you're wondering why that happens, this is the #1 reason. If you have an open source model, you can adjust the temperature to whatever you want. For example, ChatGPT, they prevent you from going higher than 2 because they don't want you to get crazy answers out of running ChatGPT. So the temperature variable comes here in softmax. Question?
Why even use the softmax? Why not just use the values?
Oh, okay. So the question is, why even use softmax? So the reason we need it is because we need to normalize the function. You could have basically 50,000, 100,000 different numbers here. We want to basically create this a probability distribution, and we're going to pick the word that is the most important word to write the next word. Right, so the softmax is just a way to take the numbers to normalize that. It makes the important ones stick out, and it makes the unimportant ones go down.
I can see that from the original.
Yeah, right, but these are only, you can see this from the original, he said, but these are only 4 words. If I had 10,000 words, it becomes very hard to distinguish the ones that are really important from the ones that are not important. Softmax makes the important ones stick out. It makes the ones that are not important quiet down. So then the neural network very easily picks the right one. If you have a high temperature, it can't do that. It just can't distinguish one from the next, and it will start to hallucinate. That's a great question. Yeah. Okay, so we've got our dot product. The result of that dot product after softmax is something we call the attention matrix. The attention matrix is basically the encoding of the context of your sentence. It's a way to encode it. What we need to do now is combine it with the original sentence. So the V matrix neural network passes it through. It does another multiplication. Think of a way as just connecting. It just connects the original sentence to your attention scores, and now we get a result that tells us with the original words, here's the attention, here's the meaning encoded of our sentence. So the attention head is very, very effective at just understanding the context, and then it attaches it back to the original sentence. So you can think of the attention mechanism, I think of it like a context brain. It figures out the meaning and context of entire long passages by looking around at all the other words, however many you want. So that's basically what attention does. Now, we talked about the encoder here on the left. You'll notice that the decoder has all those same components up above. The only thing different is that the decoder now creates words. It's actually going there and generating new tokens, new words, to write things out for you. Okay, so let's take a little bit of a peek into the decoder, and we'll see how it works. So let's say you've got your prompt, you've written it into ChatGPT. It's turning into tokens, it's turning into embedding, so it's understanding mathematically what it all means. So it goes through all those same things we just saw. So it's got your attention heads, it's got all the softmax, all that stuff we just saw. Now, what it does differently is it goes now and says, what is the next word likely to be, considering this context? So who is Snow White? Well, the next word is, Snow White is a fairy tale character from, and one word at a time, it starts to generate new tokens. So encoding all of this into that matrix, it goes out there, we shift right, and we generate a new token. Now, we need to do a positional encoding because we need to figure out where this new token should be in this long list. And then it passes it back up and goes through the whole thing again. So do you know how if you type ChatGPT, you can see it coming at one word at a time, bam, 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 bam. It's creating words linearly as it goes through. What it's doing is it's cycling through this algorithm over and over and over again, very, very quickly, right? So it's going quickly through this algorithm, and every word it generates, guess what it has to do? It has to go back to the beginning and look at everything it wrote. So it's like you're writing a letter or you're writing an email, and every word you write, you have to go back to the beginning and read the whole email to make sure it still makes sense. So that's what this decoder is doing. Every new token that gets generated, it goes back again and again and again to make sure everything makes sense, and we're creating new attention scores every time we go through. Now, at a certain point, it gets to the point where it says, you know what, I've written enough. This whole thing makes a lot of sense. I don't need to write anymore. And it generates a new token called EOS. And that token stands for end of sequence. It means that this is the end. I do not need to write any more tokens, and it's considered as finished. So at this point, we're done, and it stops creating content for you. So that's what the decoder does. It's very simple. It's basically the encoder with just a generation piece and positional encoding. So that's what a transformer is. Now, what if I have more than one transformer? So this is what we see in most modern language models. For example, GPT-4, even 3.5, they have 96 layers of the transformer. 96 layers. So in the first layer, it's generating, it's discovering things. The reason we go layer by layer by layer, why do we do all these transformers? It gets deeper and deeper insights into what is written, and it refines it more and more each time it goes through. Okay, so why 96? It just seems to work. Nobody really has a science around this. They just test it until it comes up with a certain number. Gemini from Google, they have like 118 layers. Every model is going to have a different number of transformers all stacked. So what we went through is the architecture of the transformer, but the reality is that there's a lot of transformers at work into these massive models. Every one of them has the attention mechanism. So this brings us to our second innovation of DeepSeek. Every time you go through the attention mechanism, it's going to be computationally expensive. You're using a lot of GPUs to calculate those attention scores. Now, if I've got all these decoder blocks, 96 layers of it, do I really need to calculate attention over and over and over again for everything I've already done? So you know what DeepSeek did? They said, why don't we just cache the attention score and pass it from one block to the next all the way up? Now, in ChatGPT, we don't do that. We actually go back and calculate the attention score over and over and over again at every layer. The guys at DeepSeek said, well, let's just cache it, and we're going to use it all the way through. And guess what? It works. It makes it so much more efficient than going back and doing this over and over and over again. So we talked about already two innovations. One was their floating point numbers. They're able to use a much smaller floating point number on the weights on the neurons. The second one is the caching of what we call the KV pairs. So this is the attention pairs as we go through all these decoder blocks. The third thing they do was a very interesting idea. We get into this problem with transformers. Transformers are great. Everyone's using transformers. Like every AI scientist in the world right now is working on transformers. But there's a limit. We know that there's limits to what the transformer can do. So we call this the quadratic self-attention complexity problem, which means if you increase your context window too much, you're quadratically increasing the computational cost. So if I was to increase it by 10, if I add 10 times, it's actually going to be like 100 times more computational cost. If I increase by 100, it's 1,000 times more. It's 1,000,000 times more computational cost. So this is quadratic expansion in the computational cost in the transformer. So we know that there's going to be a limit. You cannot continually add more context window. There's been a very promising paper called Mamba. Mamba uses a very different model. It's using a linear time sequence model where we don't have this problem of quadratic limitations on the transformer. It's still in the scientific research community. But the guys at DeepSeek had a very interesting idea. They said, instead of having this huge big model with 1 trillion parameters, what happens in ChatGPT, if a token comes into the model, that token hits every neuron and every parameter in the entire model every single time. So you're lighting up 1 trillion parameters every token you pass into it. The guys at DeepSeek said, well, if I'm asking a question about coding, do I really need to go to this section of the neural network about food and beverages and wine? Probably not. So they use this routing mechanism called a mixture of experts. So as your token or your whole sequence comes in, they decide what is the question about, and it routes it to the right part of the transformer. So it doesn't light up every single neuron, every single parameter, every token that comes in. They're using literally 5% of their neural network for every token that comes in, depending on what has been asked. So they're using sort of an intelligent routing into the thing. And it's kind of similar, in the brain, when they do sensors on the brain to see how you respond to stimulus. They can see different parts of your brain stimulate when you see a picture of like a beach or a picture of something that scares you. Different parts of your brain light up. Your whole brain doesn't light up equally. Well, GPT-4 and these type of transformers, everything lights up every time. So the guys at DeepSeek, they said, well, let's just route it to the part of the transformer that can answer that question. And they reduced the significantly amount of GPU that was required. So again, those three innovations are reducing the floating point numbers, using the KV caching in the attention mechanism, and then lastly, this mixture of experts allows it to be massively more efficient. They were able to publish the results. I've read their paper very thoroughly. I wrote a blog on it, and it's convincing. It makes sense what they did. There's no mystery about how they did it. It's all been published. It won't be long before LLaMA and Gemini and OpenAI, they're doing the same thing. Give them 6 months, and they'll be doing exactly the same thing. It's in the open community now how they did this. We're just going to see more and more innovations, I think, in neural networks and these kind of models to let us do more things. Okay, so let's, we've gone through the transformer. We looked at how it works and what it's doing. We're going to look at a little bit of adaptations. So how do we use these models to do exactly what we want with them? So for example, at Cisco, we're using these kind of models for TAC. We're using them in enterprise networking and Catalyst Center. We're using it in Meraki Dashboard now. We're using it in security, WebEx, all these different places. You want your model to be intelligent and respond to your type of questions. It has to know the context of your situation. There's two ways to do that. One is fine-tuning. So fine-tuning a model means that you go in and you relearn parameters of that model. So do you remember the picture of the neural network I showed you with all those circles and all the weights? Okay, the weights are where the training lives, right? The weights and the bias is what is learned as it passes through information. If I wanted to do a very customized model, so I want to train it, for example, let's say I'm a hospital, and I want to train it on our patient data, on medical procedures, on medications, that may not be in ChatGPT. So I'm going to get an open source model, like LLaMA, like Mistral, or something like that, or DeepSeek if you want, and I'm going to now pass it new data. So I'm passing it all this new data, and it's looking at all these documents, looking over and over and over again, and it's training those weights on the existing model. Now, we don't erase those weights and start from scratch. What we do is just give it new information. So we're changing those weights on that model. That can be expensive because, again, if it's a trillion parameter model, this could be a very, very long time. Typically, we'll use a smaller model. For example, LLaMA, you might use a 3 billion parameter model. You can do it much faster and retrain those weights. There's also a lot of new breakthroughs that have happened recently. There's something called LoRa, low rank adaptation. It's a way to actually add a new layer to your transformer. And this is where your new information will be learned. You keep the rest of it the same. You're just adding a new layer where your new information gets stored, and it will train very, very fast. So fine-tuning is a very popular way to do it, but you have to touch the model. The other option is called Retrieval Augmented Generation, or RAG. RAG and fine-tuning are often used together. Like, people call RAG as fine-tuning. It's not. RAG is not fine-tuning. RAG is a way to give your model more context. It's helping it answer, but you're not changing the model. You're not changing a single parameter on that model. You're just giving it more information. So as an example of fine-tuning, so let's say I have a base model like this, and let's say I'm a medical clinician. So I'm going to ask the model, please help me diagnose this. A patient complains of fever, cough, and difficulty breathing. So I go and download an open source model, and it gives me a very basic kind of output. Oh, could it be common flu, pneumonia, COVID-19, bronchitis, asthma? I'd like a little more information if I'm a doctor. Right? This is too limited. So I go and I feed it a whole bunch of medical reports, and I give it more documents, and I tell it how I want it to respond. And this would be an example of the same model, but now it's fine-tuned. So I've fed it more training data. It relearns the weights, so it augments and changes the weights, or maybe I add a new layer. And now it gives me a much more comprehensive output of what I want to see. So this is what fine-tuning is able to do. And we see our customers wanting to do this all the time. I'm working with a customer now that is trying to talk to their NetFlow collector. So they want the NetFlow collector to answer questions about flows, about ports, about how many people hit their website, all these kind of things. And there's really no model out there that's well-trained on NetFlow. So what are they doing? They're fine-tuning. They're giving lots and lots and lots of examples of how they want the model to respond when they ask questions. So fine-tuning is very powerful. Now, RAG, on the other hand, it's about giving more context to the model, so it helps it to answer without changing the model. So here's an example, just to make it intuitive for you. So let's say you go to your model, and you're going to ask it to respond in a certain way. So I'm going to condition the model. I'm going to train it, prepare it to answer the right way. I'm not changing the model. I'm just kind of teaching it through my prompt. So this is using Gemini. So I want to give you some movie reviews. I'd like you to classify these reviews in 3 categories. Rob loves the movie. Rob hates the movie. We're not sure how Rob feels about the movie. And then Gemini says, OK, sounds good. I'd be glad to help you. And I'm going to answer in that format. So I say, OK, I just saw the new Ferrari movie. What a bore. Acting was terrible, and the story was lame. Not a fun for a true Formula One fan. OK, so how does it say? I can adjust Rob hates the movie. Very simple, because I've conditioned it. Right? I've given it context how I want it to answer. I didn't retrain anything. I just told it how to answer. So if you can give more context, it knows what to do. So do it again. So I just saw Dune 2. It was pretty good, but could have been better. We're not sure how Rob feels about the movie, right? So it's picking the right category that I had conditioned it with. Here's my first reviewer. I just saw the new Planet of the Apes movie. It was really exciting and not a bore at all. It says Rob loves the movie. So this is called prompt engineering, as you probably know. So prompt engineering is about giving a context to how you would like it to respond. RAG uses that idea. So what RAG does is I go to my chatbot and I put in a question. And let's say I want a question about NetFlow, right? Or about our particular company or something like that. So we do the normal steps. We take our question, we tokenize it, we do the word embedding, so we turn it into our vector. Now, instead of giving it right to the model doesn't know how to answer, right? Because it doesn't know anything about our company, it doesn't know about our NetFlow records and these kind of things. So it goes to an intermediary step called a retriever, and the retriever says, you know, the information you're looking for, we've got it stored in a database. We call this a vector database. And this vector database has all the documents you ever would need to answer the question. It's like going to the library. The library has all these books, and there's a book there that has the answer to your question. Now, all the documents here are vectorized, right? Word embedding, so we've talked about how we turn words to numbers. That's why we call it a vector database, because all the documents have been vectorized. So the retriever says, okay, I'm going to go to the vector database. Which document correctly answers the question that you just asked me? So it searches through the vector database, and he says, I found the right document. This is the one that answers the question about your query. And it brings it back, and it combines them together, your query, your prompt, with that document. Technically, it's called a chunk, but you know, that's for another day. So it combines your question and the right chunk, right document, and it sends it to the language model, and it says, here's the question, and here's some supporting information to help you answer it. And it searches through it, it combines it with its own training, and it goes back and he says, here's the answer that I got, and it seems magically to be able to answer a question, even though it's never been trained on it. That's what RAG is all about. RAG is about giving it context that sits on the side. So what's better, fine-tuning or RAG? Well, there's pros and cons to both. Fine-tuning can be expensive. It can take a long time. You don't want to fine-tune your model every day. Just when new information comes out, do you really want to go and fine-tune a model? Well, you're going to use a lot of GPUs, it's going to be very expensive. I do want to fine-tune it sometimes because I'd like to get the structure and the format right, but as new documents become available, this is a cheap and easy way to do it. All I have to do is add a new document to the library, to my vector database, and I can keep it updated very, very fast. Which one is going to be performance-wise better? Well, fine-tuning is better. There's an extra step here of going to the vector database that slows me down, so you will have a performance impact from using a vector database and RAG, but you have the flexibility of being able to add any documents you want. Now, you might be wondering, how is it picking the right document? How is it figuring out what's the right document that answers my question? There's a neat little algorithm called cosine similarity. So it's using, remember that vector space I showed you with all the words floating around in space? It's basically using that idea. So it takes the word embedding from my prompt, whatever I put in, and it's looking into the vector space, and it sees, for example, all these different words that could be there. Which word is closest to the document that's in the library? And it discovers, well, there's probably different words that are really, really similar. The ones that have the closest vector will be the document that we take out of the vector database. So why is it called cosine similarity? Because the cosine of 0 is 1. So if the angle is 0, we get a 1. So it's going to look at every document, look at its cosine similarity. The one that's closest to the value of 1, that is the document we pull out and combine to go into the language model. All right, so we're using semantic similarity search, cosine similarity. Okay, so that's how RAG and fine-tuning work. How are we using these kind of things at Cisco, and what sort of opportunities have we found from the transformer? Well, we're using it across our portfolio and many different products. First I'll talk about is in WebEx. So just about a year ago, we introduced something called the WebEx AI codec. And of course, it was very trendy to call everything AI. AI sounds like, if it's got AI on it, it must be good, right? Even I was suspicious at first, like, what does that actually mean, an AI codec? Come on, really? But there's a real story behind this. So to make this intuitive, you may have heard this story about the Beatles. So they had their last song. It came out about 1.5 years ago. It was called Now and Then. And there's a really interesting story behind this song. So before John Lennon died, he had recorded this song. at home on his piano. It was a very, very bad recording. And then, of course, he was killed. But Yoko Ono took that recording and gave it to Paul McCartney and said, can you do anything with this song? And turned it into a Beatles song. And this was, of course, 1980s. Technology wasn't very good back in the 80s, and nothing happened for a long time. And then about 3 years ago, Peter Jackson, who did the Lord of the Rings films, he was working with the Beatles on a documentary. And Paul McCartney says to him, we've got this old recording from John Lennon. Is there anything that AI can do to make this better? And of course, that was when the Transformer was starting to come out. And they looked at this and they said, well, yeah, we can use generative AI, not for words, but for spoken language, like spoken audio, to recreate John Lennon's voice. So this is not about cleaning up the signal. This is about recreating John Lennon's voice according to that melody. So this is exactly what we do in the WebEx AI codec. Just like that song, Now and Then, there is a transformer that takes the encoder. So we're taking the audio input, the sound. I talked about the smallest, what's the smallest component of a word, again, in language modeling? What's it called? It's called token, right? What's the smallest component of a picture? So naturally, we're going to say pixel, right? But it's a little bit, almost a pixel. It's called a patch. A patch is a collection, like a 16 by 16 collection of pixels. Like a token is not always a letter. It's actually multiple letters to make a small component of a word. A pixel is a little too small, so a patch would be a collection of pixels. In the world of audio, what's the smallest component? It's called a phoneme. So think about a token, a phoneme, a patch, they're all the same thing. They're the smallest component that goes into the transformer. So we've got a transformer in WebEx that's trained on audio voices, just like the one for John Lennon was trained. So the input comes in as an audio signal. We encode it. We go through generative AI. We're actually now creating new phonemes and creating new sounds. So inside, just like we have an embedding model for words and tokens, there's an embedding model for phonemes. So when you talk, as we intonate the voice, one phoneme leads to the next. You can predict the next if you've been trained on a certain sequence. So if you train on a human voice, your voice, it will sound exactly like you. That's how they did it with John Lennon's voice. It wasn't a cleaning up the signal. That's old technology. The transformer is about creating new phonemes and new audio. So how does this compare with other types of audio codecs? So I want to show you this example. So we actually compared this with the sort of the top open source codecs out there in the industry. So Opus is a really well-known codec. So this is in the open source community. So this is Opus running around 9 kilobits per second. So I want you to listen, and we'll make sure our audio Lawrence there is working for us at the back. We're going to listen to what Opus sounds like at 9 kilobits per second. This is not AI yet, right? This is the open source community. This is what it sounds like.
Supper and some clean straw to lie on in the cowshed. At the break of day, Yvonne awoke to the sound of the giant's.
Okay, how would you evaluate that sound? Would you give it 10 out of 10? It's not really. There was a little crackly. There wasn't a bass. There wasn't much quality to the voice. Maybe a 4 out of 10, maybe a 5 out of 10. But it was okay. It's passable, but I would not say it's high definition. So let's go even lower. Now let's go Opus compressed. There it is. If I can find my mouse. Where did the mouse go? Let's go back, go forward, and find the mouse again. Am I blind? Oh, there it is. So, on the screen, it doesn't show up over here. You're all thinking, like, why can't Rob see that stupid mouse? It's like, is he blind? Because on this screen, it's not showing, but on this screen, it's like right there. Okay, so let's listen to the same one, now compressed down to 6 kilobits per second.
Supper and some clean straw to lie on in the cowshed. At the break of day, Yvonne awoke to the sound of the giant's.
Okay, is that better or worse? Way worse, right? Terrible, because it's compressed. It's compressed audio. Now let's use WebEx AI codec that's using a transformer to actually generate the phonemes of that voice. And we'll look over here. And so we're going to do it way, way down there, and we're going to be running this at 1.6 kilobits per second. Okay, so we started at 9, we go to 6, we're now going to 1.6. 1.6 kilobits per second using the AI codec and using a transformer. Oh, went the wrong way. Here we go.
Supper and some clean straw to lie on in the cowshed. At the break of day, Yvonne awoke to the sound of the giant
How did that sound? Much better. Much, much better. And that's at 1.6 kilobits per second. That's what generative AI can do in audio. So you can see that this is very different from just trying to compress a signal to clean up a signal. This is a very, very interesting way to approach it. Now, modern WebEx, this is what you have in your WebEx calling. Why is it important to have good quality voice? Well, with voice, I can now transcribe it. I can do words to text. Once I have the text, I can translate it to any language I want using another generative AI transformer. If you don't have a good codec, you cannot do any of those things. You cannot have a good call center agent. You cannot deal with any of these types of new technologies we're using in collaboration. That's the power of generative AI for audio. Let's take another example in security. So there's a product we have called Email Threat Defense. We had acquired a company about 1.5 years ago called Armor Blocks, and their mission was really to look at emails and look at how to use generative AI to protect against phishing attacks. What we find today, even the most common threat into networks is email. So phishing attacks, we see spear phishing, impersonation attacks, malware gets attached to these links. It's very hard to keep up to email attacks because they change the links all the time. They look absolutely authentic. Very, very hard to identify a phishing attack from anything else. But if we were to use generative AI and look at the words of an email, pass it into the language model, what can the language model do? Well, it can tell us, because it's been trained on millions and millions of emails and millions of phishing attacks, it can tell you much better than a human can if this is a phishing attack, if it's a threatening attack, but it can do more than that. It can tell you that this is intimidation, this is extortion, this is theft of identity, just by looking at the language, just the words of the email. Most email systems out there that do protection, from all of our competitors, what do? They look at the link of the email inside, they look at the attachment, they unzip the attachment to see if there's malware in it. They're not looking at the words of the email itself. What we're doing is passing it into a generative model, a language model that looks at those words. Now, do you remember I said there's two classes of models? There's the encoder type and then the decoder type. So ChatGPT is like a decoder because it's generating tokens. If I'm just reading an email, all I have to do is just read it really, really fast and tell you if this is good or bad. That's an encoder only. So the most popular encoder model out there is called BERT. So it's an open source model, but that's essentially what we're using. I want to show you how it works. So let's go for a little demo here. And I'm going to go to PowerPoint. It should be coming up. Good. And let's go to threat defense. So this is email threat defense. So this is the product that came from Armor Blocks, but it's now been combined with Cisco's existing email security platform. And by the way, the guy who was the founder, the two founders of Armor Blocks, they're now leading all of AI at Cisco. So DJ Sampath and Anand Rakhavan, they're the leaders of AI. They're developing all of the AI technology at Cisco. So it's an acquisition that, we got more than just a product. We got a lot of talent in the industry. What we're looking at here is the dashboard for email threat defense, and we see that there's different classes of phishing attacks, there's malicious, there's scams. Let's go dig into one of these. So we're going to look at these different emails. You see they're quarantined, that the emails have been quarantined and stopped from getting to the user because we see something in the words of the email that is inappropriate. So let's go and take a little example. So let's go look at this one here from John Hammond, straight from Jurassic Park. Okay. So do you notice there's different classes here? There's a user impersonation. So it sees by looking at just the pure words, it's been trained on how people use email and use certain words. It says, well, this is words from a sender that doesn't look like that sender. It's being impersonated by someone else. We see here that there's a rare sender domain for recipient domain. So we've never seen an email from this person before. Urgency. Do you know you get an email sometime that says you have to file your taxes or the government will sue you or the police will come? We get these all the time. All these very threatening emails. Please click here. And there's, older people, your parents, even kids, they're scared, so they're going to click on that link because it's intimidation. Well, the words in the email are what indicate intimidation and urgency or threat. This is what we can pick up from the language model. So what kind of a language model are we using here? It's an encoder type of language model. So a BERT-style model, it simply has to look at the emails and incredibly fast. Encoders, because they don't generate tokens, they tend to be orders of magnitude faster in how they classify, and it will classify into one of these things. Email threat defense has over 100 classes of what the email can be doing, what it's about. Is it extortion? Is it data exfiltration? Is it whatever? We have over 100 classes that we just look at the words of the email and tell you what's happening. So this is a very, very effective way to do email protection, not just looking at the links, which change all the time, or the attachments, but right in what the email had actually said. Let's go back to the presentation. Okay. So the last area I want to talk about is an enterprise networking. So how are we using generative AI in our product? So if you, excuse me, if you went to the keynote, you would have seen examples of a smart chatbot that we've been developing at Cisco. So we're starting to see chatbots show up in various places. So we see them in different security platforms, in different enterprise platforms. It's been the vision of Jeetu Patel, who runs all of engineering at Cisco. We want to have a unified AI chatbot. And this is very, very exciting because it's like every product can have its own GUI. Every product can have its own chatbot as well. But isn't it better if these chatbots are synchronized and can talk to each other across product? Give an example. Why is WebEx slow through your firewall right now? Is that a WebEx question? Or is it a firewall question? Or is it a secure access question? Or is it a DNS question? Who knows? It could be all of those things. So if you're going to build a chatbot, you want one that understands the complexity of all those different products. So what we're building is a unified AI ops assistant that can interpret the question that you write. So the first thing it does is says, okay, this is a question about WebEx, and it seems to be slow. There's all these possible reasons WebEx could be slow, and it understands your network. And it's connected to security. It's going to be able to look at data in Splunk. It can look at observability. It can do different systems. And it starts to go out there and make API calls to the different backend systems. And it pulls the data that it needs, it analyzes it, puts it back into the language model, and helps you solve it and troubleshoot it. That's what a cross-product, cross-domain AI chatbot is able to do. And this was presented at Cisco Live last summer in Las Vegas on the keynote stage. This is the ambition that Jeetu's team has, and we have that entire team that's building this thing now. So what kind of problems would I solve with a unified AI assistant? Well, really, there's 4 main classes of use case. The first one is just knowledge-based questions. So how do I set up SDA? How do I add a user to ICE? Can you please tell me Cisco licensing? I don't understand it, and it's really complicated. This is knowledge, as everyone's, even I asked that question. This is a typical question, type we'd ask. Those are knowledge-based. Now, what are we going to do for this? Probably RAG, right? RAG would make a lot of sense because these documents and instructions are going to change all the time. So RAG would be the typical way you answer questions, knowledge-based questions. A second use case is just talk to your network. Like, network, how many firewall rules do I have right now? Oh, you have 80,000 rules. Which rules have not been hit in the last 30 days? Well, you have 80,000, you have 78,000 have not been hit. Why have they not been hit? So asking questions of your network, it interprets what you asked. It goes out there, it creates an API call incredibly fast, pulls out the data, and gives you an answer. So just talk to your network, ask questions about my network. Imagine you have one chatbot that I can ask questions on any Cisco product. Right? That's our vision of the unified AI assistant. Second one is troubleshooting. Now we're getting more complicated. This is hard. Troubleshooting, it gets, exponentially more difficult because there's many ways you can troubleshoot. This WebEx is slow through my firewall question. There could be 1,000 reasons why it's acting very, very slow right now. Well, troubleshooting means workflows. There's a certain process that has to be followed, a certain workflow we need to understand and go and execute these things. If I do the workflow wrong, I might give the wrong answer. This will take more time. So as we are developing this, the two easy ones that you'll see very soon are this bottom one and talking to your network. But troubleshooting is something we're working on as well. So with TAC, of course, we're working on how to do these troubleshooting. But then the last one will be automation. So, Mr. Chatbot, I'd like to please provision a new overlay or a new SD-WAN connection. Please go and create that. Oh, and send it to ServiceNow, too, so we have some change control management. So just one word of English, one sentence of English, rather, and it should be able to go and create that entire automation script. This work as well is underway. So we're going to see all these types of innovations in a unified chatbot in the the next couple of quarters and years. It's a multi-year project. Don't expect this all to happen in day one, but this is what is emerging. So I want to show you what we've got today. So this is what we're looking at is the Meraki dashboard. Now, even though the chatbot shows the Meraki dashboard, the intelligence on the back end is a unified AI cloud. So from Meraki dashboard, I can talk to ICE. I can talk to Catalyst Center. I can, we've even seen demonstrations now from Meraki dashboard. I can ask questions on my Cisco Firepower, my firewall, and get it back. So we're looking at this as a unified chatbot. So let's take an example. So we're going to ask it a question. Okay, so which access point is busiest right now? So this is asking a question about my network. So it has to make an API call, and it says, okay, the busiest one is San Francisco SFO 12. It's at 96.94%. That's pretty busy. Okay, I'm gonna ask another question. Well, okay, how many clients are connected to it? Even though I told the name, I didn't have to say, I could just say it would remember. It says there's 73. So there's, oops, sorry. Let's go back. Okay, there's 73. So what we're doing is we're asking questions about the network and just getting telemetry, getting these questions back. Sorry, I have to let this play out again. Now, it said that there's 73. That's a lot of clients to have on any access point. That's probably why your network is really, really high channel utilization. You've got a problem here. So if you've got a problem like that, what's the next question you're going to ask? Well, okay, well, how do I fix it, right? So now I'm going to switch the style of question from asking my network. I'm going to ask a knowledge-based question. So now I'm going to say, what's the best strategy to optimize the channel planning? And the model knows this. So it's semantically deciding if this is a question about my network or this is a knowledge-based question. So it says, okay, well, here's the best strategy to go and solve this. And basically the answer is you need to go put more access points in. Go talk to your sales rep. This is the answer. Well, that's kind of obvious. Okay, well, that implies licensing. So, what are the licensing options available? Here's your licensing options: co-term, per device, subscription. And we all have no idea what co-term actually means. So can you explain co-term licensing to me? Here's what co-term licensing is. So ChatGPT would never have this knowledge. It doesn't have this kind of knowledge. So we're not using ChatGPT. We're using a more bespoke model with a mixture of fine-tuning and RAG to be able to answer these kinds of questions. So let me ask you a question. Do you like this? Is this cool? I think this is going to change the way we manage networks. Like we're looking, in the next couple of years, the day-to-day operation of a network is not going to be through a GUI. I could do all those things through 50 clicks of my mouse to find the right images. Imagine what we're going to be able to do with this kind of unified assistant, this virtual assistant for the network. And even though we're looking at it inside the Meraki dashboard, this one will be able to talk to anything. So from Meraki, I can talk to ICE, to Catalyst Center, to vManage. All these different things are intertwined, as well as in the security side. This is all going to be completely integrated over time. So this is our vision. This is the new way of managing networks. It's going to make it way more efficient operationally. You can do more. You don't have to, this should reduce your TAC calls, to be very honest with you. This should help you find information quicker, solve problems quicker, reduce the waiting on TAC, quickly get to things very, very fast. and we don't want you to be cutting and pasting from ChatGPT and putting code in. This will all be something you can do from the Unified Assistant. So how is it going to work? So let's just take you through the architecture of this. So this is you. This is your network operator in your chatbot. So you've got an interface. This could be on Meraki. This could be on vManage. It could be on anything you have. First thing we do is we go to the cloud, and through an API, we have to figure out what's the question about. So we go to a dialog state manager. Is this a question about just a knowledge-based question? Is this a question about my network? Is it a question about troubleshooting? So the DSM, dialog state manager, figures that out. He says, okay, this is a question, say, about your network. Once we know that, which products are involved? Okay, if I know the product, then I have to make an API call to that product. So what we're going to do is we're going to go to the LLM and say, please write an API call for me. I want to go talk to, say, Catalyst Center to solve a problem. Please go write an API call to Catalyst Center, and here's what I care about. So the language model knows how to build API calls. It takes all the right fields and parameters, puts it into the API call, and it goes out there, creates the workflow, calls your API in your controller, your Catalyst Center, vManage, whatever it is, and pulls the data back. Once it's got this data back, it puts it back into the language model, gives you an answer, and you've got your solution. So it's a combination of things. It's not purely a chatbot. It's actually doing some interesting routing here. It's figuring out what's the question about, making the API call correctly, going and talking through the API. These are the mechanics that are going to be able to support cross-domain and cross-product integration. Now, let's say I'm asking a question about knowledge-based stuff. So how do I figure out Cisco licensing, co-term licensing? Please explain that to me. Well, the DSM says, okay, that's a knowledge-based question. That's not a question about your network. So it routes it to maybe the same LLM, but it instructs it to use RAG. So now we're going to pull information from the vector database. This could be very fresh, updated information, your data sheets. So as new data sheets come out, we'll immediately add it to the vector database. You get up-to-date, immediate information about whatever you want in that product, how to configure it, how to license it, the schema for that product. It will all be stored into the vector database. This is not something that ChatGPT or any other public or open source model would have. We pull this data, we send it back, and you have the answer. So architecturally, this is what we're building. So you'll be able to see some of this in Whisper Suites here at Cisco Live. You'll see some demonstrations of the World of Solutions. This is well underway. So the security one has already been launched. We have over 2,000 customers that are using the AI assistant in security. Meraki and Catalyst Center are coming out literally this month. So we're going to be able to use this day-to-day in our network. So in summary, what have we learned in our session today? This has been a bit of a whirlwind. We've covered a lot of ground, haven't we? We talked about language modeling. How does language modeling work, and how did it all come about? And we understood the importance of the transformer, how it really did transform the way that we do AI. It has changed everything that we see in modern technology, and it certainly is going to change network management. The transformer is a very flexible architecture. We can use it for, of course, language. We can use it for audio. We can use it for image generation. And at Cisco, we are heavily using that architecture in a variety of different ways. Hopefully, we made it clear, too, the differences between RAG and fine-tuning, and you can see why you would use one over the other. And it's important to know that distinction because you're going to be probably exposed to it and using it. And lastly, expect a lot of this to come from us in the next couple of quarters. So starting today and moving forward, you're going to see huge adoption of this technology across our portfolio. So hopefully you guys enjoyed that and you learned something new. Thank you so much for coming. Please fill out the survey. I'd love to hear your feedback and have a great rest of the show.